Welcome to Forces, Universal Law of Gravity. So what is the universal law of gravity? The universal law of gravity states that is basically that there's any two objects that have mass attract each other. So we've always known that we're pulled down by the earth, but what isn't always highlighted is that when we're standing on the earth is pulling down on us, but we are also pulling up on the earth with equal force, according basically off of Newton's third law, correct? Okay, so the value of g, the acceleration due to gravity, is 9.8 meters per second squared down. It's special. It is a measured value that applies to objects on or near Earth's surface. This means that the value for g could not be used for objects located significantly above or below the average radius of the Earth, or for objects located on other astronomical objects, like planets, dwarf planets, and asteroids. In fact, if you go to the top of Mount Everest, you actually weigh slightly less than you do at sea level, because you're further away from the surface of the Earth, or from the center of mass of the Earth. Okay, how do we find the force of gravitational attraction between the Earth and the Moon, between the Earth and the Sun, or between you and your physics textbook? Newton to the rescue. Newton proved, using calculus, that objects of finite size, objects that can be measured, even if they are very large, can be considered as particles. That is, even the largest of objects can be considered as a point, with all its mass at one point, usually the center of the object. So, for example, here is the Earth. Let's say this is the Earth. I'm not a very good artist, but here's the Earth. This can be, and we know that the Earth has a certain amount of mass of Earth. This can be looked at as a point in space, a point, and all the mass is focused on that one point. Okay, so the universal law of gravity, the mass of the Earth is 5.972 times 10 to the 24 kilograms. Okay, and this can be illustrated, or you can view this in terms of the universal law of gravity as a point. So here's a point that has a mass of 5.972 times 10 to the 24th kilograms. Using this fact and the facts that the force of gravitational attraction is proportional to the masses of both objects in question and inversely proportional to the distance between them squared, we can develop a proportional statement. So what Newton discovered is that the force of attraction, gravitational attraction between two objects, is proportional to both the masses of the objects. So the mass of object 1 and the mass of object 2. And that it's inversely proportional to the radius squared. Okay. So in this case, if you were looking at yourself on the surface of the Earth, if we were to draw both of those things as a point, I'm going to change the color here. So the Earth could be viewed as this point, and you could be viewed as this point. So then if we erased everything else, we could say that here, this is the mass of the Earth, and here's the mass of the person. And so here's the Earth, and here's the person. And this distance here is r. So if you put all those values into here, you would find out that this force is proportional, but it's not equal. Newton had to come up to discover what the constant was that would make this an equivalent expression. Okay, but this is not an equality. For the two sides to be equal, we need to factor in the universal gravitational constant. So here's the universal gravitational constant. It's a very small number. You can see that it's 10 to the negative 11. And then here's the units, okay? Notice the universal gravitational constant is a capital G, whereas the Earth's gravitational constant is lowercase g, the acceleration due to gravity, that is. Think the universe is bigger, so it has a bigger g. So now we have a formula for the force of gravitational attraction between any two objects. And that's F of sub g is equal to the constant g, which was this value right here, times the mass of object 1 times the mass of object 2, divided by the distance between the two objects, squared. Okay, let's do an example. Let's see how the attracted two members of our class are to each other. Okay, so if we have one student is 65 kilograms and another student is 85 kilograms, and let's say that they're 1.5 meters apart from each other, what's the force of attraction, or gravitational force, between those two objects? So if we plug this into our equation, we have our constant, 6.67 times 10 to the negative 11. We have the mass of student 1, the mass of student 2, and the distance between them. Now notice that we're able to cancel units. So here we have kilograms cancels with one of these kilograms, and the second kilogram cancels with this one, getting rid of the kilograms. And then notice up here that you have meters squared, and down here you have meters squared, so those cancel. So when you cancel all the units, you're going to be left with just newtons, which is what we want. And if you multiply all this out, you have the force of gravity between the two students is 1.63 times 10 to the negative 7 newtons, which is a very small number, which makes sense because when somebody walks by you, you don't automatically get pulled towards them, and they don't get pulled towards you. But both classmates are attracted to each other with a force of 1.6 times 10 to the negative 7 newtons towards the other student's center of mass. And keep in mind that the universal force of gravitation, this is one of the fourth universal force of universal forces, and it's the weakest of them. And so it's only significant when you have an object of a large mass, like the Earth. This equation works for any two objects in the universe. Determine the force of gravity between the Earth and the Sun. So here we have some larger masses, and we'll have a more significant force. The force of gravity between, so here we have the universal law of gravitational, the universal gravitational constant. Here we have the mass of the Earth. Here we have the mass of the Sun. And here we have the distance between them squared. And when we multiply that out, we get a much larger number, 2.092 times 10 to the 22nd newtons. So the Earth and Sun each experience a force of gravity of 2.1 times 10 to the 22nd newtons toward each other's center. And that's why, that attraction keeps the moon orbiting the Earth. Any questions?